Yes, I'm able to see.
Yeah, so I'll present the paper uh, of verifying neural networks against backdoor attacks.
Go ahead.
So, so this is the overview of this presentation. So I'll informally introduce the problem and the motivation to solve this problem. And then I look at formalizing the problem and see what the challenges are, and then walk through a very simple example of how this paper tries to solve it.
Mm.
And then we'll actually look at the technical approach in its full detail. Um, and we'll also look at the correctness and soundness arguments the paper gives for this approach. And then we look at the experiments they have run, the methodology that they have used, and the results of those experiments. Finally, I'll just summarize and look at the limitations and which will uh, suggest what the future could look like. So, so the problem is about backdoor attack. So a backdoor attack involves just a second. Yeah, so it involves embedding a trigger into a input that goes into a neural network with the idea that the network will produce a very specific target output that the attacker chose ahead of time. For example, if you see on the right, you have an input 7 from MNIST, and if you feed it into a network, it outputs 7 as you expect. But on the right, if you have the same input 7, but with a slight modified patch, that is the backdoor trigger. And when you feed this in, the network will output 8. And so this is a backdoored network because you can expect it to do it consistently with multiple images with the same backdoor patch presenting the input. So one way to do this is like through data poisoning. So on the left, you can see where some label and input pairs are modified. The label is modified to a target label. Like in this case, it's 8. This is what the attacker wants to
You
target.
use the term, what did you call it? Data posing, is it?
Sorry, data poisoning.
Data poisoning. Yeah.
Yeah.
The training data poisoning.
Yes.
Yeah.
Sir.
You may want to say training data poisoning.
Yeah. So one effective way to do is training data poisoning, where you choose a target label. In this case, it's label 8, and you choose a specific trigger that is, okay, I want this pattern with this shape in this location of the input image. And you modify the training data and you train the neural network on this. And this neural network behaves normally when there is, by normally, I mean as expected, like an MNIST classifier when there is no trigger. But when there is a trigger, you'll consistently see the target label being output, no matter what the input image looks like. So the problem is, given a neural network, we want to verify if it's whether it's free of such backdoors with a certain level of success rate. We talk about certain level of success rate because backdoor attacks are usually not 100% successful. So for a realistic method, for a realistic problem, we need to consider the case where it might not be 100% effective, maybe it's 80% effective, and we still want to verify that the neural network does not have such backdoors.
Good. Go ahead.
Yeah. So the motivation to solve this problem is, so neural networks are becoming more and more capable, and therefore they're being used across the industry in many applications, which also happen to be safety and security critical, like face recognition, diagnosing medical images, autonomous vehicles, and so on. And the defense approaches to backdoor attacks are limited.
What do you mean defense approaches? Existing defense approaches?
What I mean is approaches that try to prevent backdoor attacks or to detect backdoor attacks.
Ah, okay. Existing approaches, yeah. Okay.
Yeah,
Defense approaches, I understand what you mean, yeah.
Yeah.
To defend against backdoor attacks, that's what
Yes.
you mean. Yeah, okay.
Yes.
Please go ahead. Yeah.
So they're limited in the sense that their paper claims there are almost no methods that will provide a formal guarantee.
Mhm.
So most of them are usually empirical based. And they say there's one work that comes close to certifying the absence of backdoors, which relies on randomized smoothing. I haven't read that particular paper, but the paper, this author claims that it degrades the neural network's accuracy because you modify the neural network to get a smoothed version of, you get a smoothed version that is supposed to be resilient to attacks. So the main contributions of this paper is that they provide a novel approach to verify formally that there are no backdoor attacks in a given neural network with a specific success rate. And it also has few
Limitations.
limitations or catches. Like, so there are some certain constraints on the trigger, like what size the trigger could be. So the proposed method is a combination of two ideas: statistical sampling idea and an abstract interpretation idea. We need statistical sampling because we're involving a formal guarantee, but with the probabilistic
Success rate, very good. That's
estimate.
exactly right. Yes.
And we use abstract interpretation because exact methods will require exploring a combinatorially large space because we don't know what the trigger content is.
Yes. Okay. You may want to draw parallel to deep poly and abstract interpretation. Deep poly uses, no? So you may want to.
Yeah.
Just
Yeah.
mention, I mean, something like as used in deep poly. Okay.
Yes.
Go ahead.
Yes.
Please. So far, so good. Go ahead.
So it also includes an optimization technique. In the case this solution determines that, oh, this network is backdoored, it would be nice to generate a concrete trigger to show that this is the trigger that works on this network with the specified success rate. So what it uses is a gradient descent-based optimization approach to generate such concrete triggers if the verification fails to prove that there is no backdoor.
Yes, good.
So to introduce notation that we'll use in the rest of the paper presentation. So we'll use N to denote the neural network, a classifier to be more specific. So M is the number of input features and N is the number of output labels. So in MNIST, this would correspond to M being 784 because it's a 28 by 28 image, and N being 10 because there are 10 classes. And we have the label assigning function, which takes in this Y bar, which is a vector of logits that's output by the network. And it simply takes the index corresponding to the largest logit. Because if you do a softmax, that's the index that will also have the largest probability mass.
Yeah.
And then we'll use I to represent an input image. And since that's the input to the neural network, it belongs to this R to the power M set. And let's denote a potential backdoor trigger with S. We can, since we are looking at image-based triggers, we can think of S as an image patch with a certain shape. We don't mention, so let's also mention the position at which this trigger might be, and we'll use this HP, WP to indicate the top left position where the trigger is stamped onto the image eye. So when you apply the trigger on the image eye, let that new stamped image be IS. So this is stamped. Stamped meaning we just replace the pixels in I with the pixels of S at the corresponding position,
Yeah.
which become a W.
So else replace the corresponding pixels. Right, got it. Yeah, and throughout the patch positioned at HPWP, it replaces for the entire patch.
Yeah.
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 There is,
And the attacker also chooses a specific target label they want to attack. We'll call it TS.
Mhm.
Maybe I want to attack, like if I'm an adversary trying to attack a network in case of a medical application, maybe I'll always want it to output, I don't know, positive in case of some disease, like no matter what the actual X-ray or something, some input looks like. So let TS be the label corresponding to the target chosen by the attacker. And we'll use theta to denote the success rate. By this, we mean if a neural network is backdoored at a success rate theta, we mean like if you take 100 images, theta percent of them you can expect to be giving you the target label.
yeah, I think maybe you can say a little more detail here. I mean, this is probability with respect to some X number of randomly sampled images. Okay.
Yeah.
Correct. That's yeah.
Yeah,
Okay.
that's
Yeah,
true.
we said 100. Yeah. Some certain number of K number of randomly sampled images. How many of them it is able to attack? Correct.
Yeah. It's the expected attack success rate.
Good.
Could
Yeah,
say.
I think it's all very clear. Yeah.
Yeah.
Mm.
So now we'll define the backdoor trigger with a specific success rate, and then we'll define the problem using that definition. So let's say a backdoor trigger S, we say it has a success rate of theta. If there is a position in the image,
yeah, I mean, what I said is described here. Fine.
Yeah.
Mm.
Such that the probability that the neural network assigns to this backdoored image the target label TS is at least theta over a given distribution, which is usually in our, let's say in our empirical test, it will be the test set of the MNIST data set. So that's what we mean by a backdoor trigger S with a certain success rate theta. So the problem now is, so you can, one thing to notice is we have separated the position from the trigger. The trigger only has corresponds to some in content for the patch that we don't know and the size of the patch. We are not including the position in there. So the problem that we now want to solve is, so okay, I'll give you a neural network. I'll also mention the shape of the trigger and the target label that I want to check backdoor attacks for, and the success rate theta. Now I want to verify that there is no trigger S of the given trigger shape at any position such that the backdoor attack achieves a success rate of at least theta. Does that make sense?
Yes.
Okay. So, so before we walk through an example or look at the solution.
No,
So
here, okay, there's one confusion that question that may come up is, and I'll ask you, go to the previous slide.
Yeah.
Yeah. So even if, it is doing, even if there exists some position, it is not the theta is only probably is being computed over all things, but even if the attack could be at different positions in different images. Okay, then right, so it doesn't be the same.
It doesn't consider that case.
It doesn't have to be in the same position. Okay, different images the same trigger can happen at different positions. Even then it will consider as it has backdoor. Correct. Yeah.
No, sir, it will consider a specific position for all the images.
Is that
But-
right? Okay,
Yeah,
that's
but we don't know what the position is. So we are saying any position.
yeah, that's what's any position. So if a success rate theta given a set of images,
Yeah.
okay, for one image, the backdoor attack could happen at one position. For another image, it can happen at another position. Because in each image there exists no. There
No,
must
sir. No,
exist
yeah. So the
a
same
single
position.
position that attacks all of them. Okay.
Yeah. Yeah.
That you make it clear there. Okay.
Yeah. Yeah.
There exists a single position that is able to attack all the images. I
Yeah.
mean, I mean, it's at the same position. It has to attack, certain number of things. That's
Theta.
the
Yeah.
problem.
Yeah.
I mean, the given thing is it important that there exists the same position attacking all of them. Yeah. Okay.
Yeah. Yeah.
Okay.
So before we look at the solution, we'll just briefly look at what the challenges are. So as I mentioned earlier, the trigger search space is very large. This could be any pattern. These are floating point pixel values. And it could be at any position in the input image.
And the content could be anything also.
Yeah.
Mm.
Yeah. That's what I mean by any pattern. Like the content could be anything. And so we can't use exact verification techniques as we have seen throughout the course because they're computationally hard and they don't scale well. And you have to be careful when you choose over approximation methods because they can lead to false alarms or inconclusive results.
Yes.
Just wasting our time if you're not careful. So, and also the goal is a bit statistical in nature. So I mentioned sample size K here, but I have not talked about it. But the idea is that there are a few hyperparameters that come into play when you do statistical testing. And it's not obvious how to set these values to, to trade off properly between, say, precision and scalability. Yeah, I'll return back to this point once I walk through the algorithm. So let's consider an example walkthrough. Suppose we have a tiny network with just two input features, two input neurons, and a few hidden layers that use value activation and two output labels. So input image would just be a 2-pixel input. Let's call it x0 and x1. And trigger, let's say it's just 1-pixel attack, 1-pixel trigger. Let's say we are looking for a trigger at the first position, x0. So its values can go from 0 to 1. This is typical for a normalized image. And yeah, the second pixel, x1, is not part of the patch. So it comes from the input image, which is usually fixed because we have those at hand. Let's say it's fixed at 0.5. So we start off with the constraint on the input layer. Let's call it pre-I. So we know x00 of the input image should lie between 0 and 1. And we know x01 of the input image should be 0.5. And let's use a target label TS and yeah, let it be 0. We want to check if there's a backdoor attack targeting this. Another goal is see if there's any trigger that is x00 and for some trigger value x00 in 0,1 interval that makes the network output label 0, which is the target.
What was the original output?
I have not talked about it here. I've talked about it in the next slide when I talk about the success condition. Is that okay, sir?
I guess it doesn't matter, no? I mean, regardless of what the original thing is, the trigger, I mean, it usually makes sense if that.
It doesn't matter.
Yeah, the intention is that it should label it something else, but it doesn't matter. Yeah.
Yeah, technically, yeah. So.
Yeah, I guess so.
Yeah.
It's yes. Yeah. If someone asks, yes. Yeah.
Yeah, that makes sense. Yes. So we have our constraint on the input layer, pre-I. So the idea is to use deep poly to propagate constraints through each layer. And we know deep poly gives exact constraints on the linear parts and gives possibly an over approximation when we have activation functions. So yeah, for each neuron at each layer, we calculate the over approximations. We keep track of the bounds using linear constraints and also concrete bounds based on the previous layer's neurons. And as you do this for each layer, you get a set of constraints that describe the network's behavior. And let's call it A sub I. And now the success condition for the backdoor attack is if the output neuron for the target label is greater than the output neuron for the other labels. Here we have only two labels. So the post condition post I becomes X out 0 greater than X out 1. In other words, the logit for the target label is greater than the logit for the non-target labels. So we have the input constraint, we have the behavior, network behavior constraint, and we have the attack success condition. And the full constraint, you just put these together and you get a phi I, which is the constraint for a successful attack on this single input image. And here, notice the trigger variable is this x00I, which is the content of the trigger, which we don't know. And now we check use a SAT solver to check if this constraint is satisfied. If unsat, we know that no trigger value can make the network output label 0. And the network is safe, at least for this specific input.
They're safe in the sense the absence of backdoor.
Yeah, safe in the sense there's no backdoor.
Mhm.
So if it is sat, then let's say solver returned a specific trigger value for x00, let's say it returned 0. So we have to check because it's an over approximation method. We need to manually check if this attack actually succeeds against the real network.
Mm.
If it does, yeah, so we can return successful trigger. We look at the other case where if it doesn't work, the algorithm that they propose still actually tries to generate a trigger using optimization approach. Yeah, but I didn't want to go into that detail at this point. I thought it would be simpler to just check the two cases of unsat and sat. So we have done this example for one single input image. And we need to verify absence across many inputs because we are looking at a particular success rate theta. So what we do is we repeat this process for multiple inputs at a batch size of k. Yeah, so we get these constraints phi I, but instead for one input.
Now, thing is, although this is for a specific input, it does, for any stamps, okay? It does do any stamp, but it is for a specific input. Okay, so
that's right. Yeah, that's correct. Yeah. Yes, sir. So yeah, so we take a batch of k images. We combine constraints.
Here, I have a question for you, okay, which might come up there too.
Yeah.
I mean, you could, in principle, verify for all inputs also here, okay?
Yeah.
As you can pose that as a SAT problem and then do it, correct?
Yeah, we can't, it won't really work in practice because.
That is right. It doesn't scale. You made that point, maybe, So you could still do it, but it is not. That's why you want to use statistical methods. I think you made that point. Maybe it's worthwhile just reminding, okay? That
yes, sir. Yeah.
Possible to encode it as a SAT, but it doesn't work. I mean, it doesn't scale, and therefore you want to use statistical method. Okay.
Yeah.
Sorry, I didn't mean to interrupt your train.
No,
of-
no,
Go
no,
ahead. Yeah.
no. Yeah, thank you. Yeah, so since we want to use the statistical approach, since we can't just verify for a large set of inputs, yeah, we take batches and we try to put the constraints together and then find a trigger that works for all images in that batch, in that set. Yeah, so I'll
So
describe.
there are two things here.
Yeah.
You're mixing up the generation of the trigger with the computing this test. There are two aspects here now. To verify the absence that satisfy a particular success rate, that is one aspect. Okay.
Yeah.
The other thing is, once if it is you're not able to successfully do it, then you want to find a trigger, right? The constraints to find a trigger that works for all images in that.
Yeah.
Okay.
Yeah.
Maybe you could separate it into two bullets. Okay. Here.
That's right. Yeah.
So that there are two problems. One is whether there is thing or not, and then in the case where there is, you're not able to successfully prove that there are no backdoor attacks with a certain success rate, then you do this. And then you're okay. I mean, here, what are the constraints that you're computing, etc.? You don't know. We'll get to that later on. But sometimes, yeah, I mean, what are the constraints? That is, there's too many things in here. Okay. I think separating these two will help. Okay? There is one problem of how do you verify statistically with a given success rate. The other thing is, if you see that there is no absence of backdoor attack with that success rate, how do I generate, find a trigger that works, that shows, that for all images, there exists a backdoor attack. Okay.
Yeah. Yeah.
Now, you're saying something more, which I don't know if you want to say here or later on, but that's up to you. Okay. It collects some information about how, it violates, for each image, it collects something where there is a violation, and then it uses that. Okay. That is thing. So if you could separate them, then it will be easier, okay, for you to, as bullets,
Yes,
sub-bullets.
sir. Yeah.
That
That makes sense.
Go ahead. Yeah.
So we just saw an example walkthrough for one single example. So, but if you want to do it
now here,
yeah,
there are already two things there. I hope you're separating them. First is this algorithm one, which computes the thing, and then you do the thing. Okay. So you might as well put in kind of an outline at this point, okay, of the rest of your talk, which I'm assuming that's how you will do. First, you're addressing algorithm one, which is how you do. I mean, whether there is a backdoor attack with a certain success rate.
Yeah.
Second, that you will find if there is, how can you generate this thing? Yeah, that is the that is you cover, and then your experiments and future work. Okay, those are the fourth that you will cover. Then this particular one is addressing the first part. Okay, as to how you check. Okay, and you could change the title there. That's my thing.
Yes.
High-level description of the overall approach. One means the title is a bit misleading. High-level description of the first, of how you check if absence with the theta. I mean, if you could use that, then it will be better. Yeah.
Okay. Yeah. Makes sense. Yeah, I'll separate it, make it more explicit.
Okay.
Yeah.
Very important thing is I want you to, in the previous slide, make it into sub-bullets. Okay, the last item. Okay.
Yeah.
And then put in a overview based on that for the rest of the talk. Okay. So then, go ahead.
Yeah. So By overall approach, I mean the outer approach where we use statistical hypothesis testing. The specific algorithm they use is called sequential probability ratio test. So the inputs to this algorithm include the network that you want to verify and the required success rate for the backdoor attack, a sample size K, which is required by the SPRT algorithm, the shape of the trigger, and the target label TS uh, um, that you're looking backdoor attack for, and other parameters that are required by hypothesis testing, like the type 1 and type 2 errors, and the indifference region. So I'm a bit unsure about if I should explain this in detail. I have a slide, but yeah, I'm not sure. Maybe when it comes to that, you can tell me.
Yeah, no, I don't think so. I think that you could do. I mean, I also kind of skipped that thing. No, I mean, if you see, if there is something that you don't want to get into, you might as well not. Okay.
Okay, okay.
There are some multiple parameters, and you can just describe what that hypothesis H1 is when you describe the algorithm. Yeah.
Yeah, yeah.
Yeah. This is something that you can skip. I mean, if you're not going to do it, don't mention it because there will be just
Questions. Yeah,
begging the question. Yeah.
yeah. So the idea of this testing algorithm is to use two competing hypotheses that are mutually exclusive. So the null hypothesis H0 is states that probability of not having an attack on a set of K sampled images is more than 1 minus theta to the power K. So this hypothesis being true refers to the case that the network is safe, because theta is the attack success rate. The probability of the attack succeeding on K images is theta to the power K. And the probability of not having that attack is 1 minus theta to the power K. And the alternative hypothesis is simply the same statement negated. So is no same statement saying the probability is no more than 1 minus theta to the power K. So yeah. So yeah, so we start with the algorithm 1, which is the SPRT algorithm. We repeatedly sample K random images, and we call verify X on it, on this set. And verify X returns either one of these three, safe, unsafe, or unknown, which correspond to verify X returns safe, as we have seen when the constraints that it generates are unset, and it returns unsafe if it can generate a concrete backdoor trigger, either using the model written by the SAT solver or by using the optimization approach to generate a trigger. And it returns unknown in other cases. And based on whether verify returns one of these three, we use the hypothesis testing algorithm to either accept H0
Yeah.
or
In the previous slide, you could actually add, which will make it better. The algorithm keep track. So maybe you can do it here. It keep tracks of the number of times. Okay, I know verify is called repeatedly.
yeah, yeah.
Track of the number of times it verify succeeds and so on, right? And that's and that is actually used then to check the accept hypothesis. Yeah.
Yeah, that's true. Yeah.
So if you could just add that, then it'll be thing, and then use SPRT as a sub bullet here. Okay.
Yeah.
So then, because those are the numbers that are required for you to apply, check these hypotheses. Yeah. Which will become clear later on. But here, that it uses N and Z, okay, that it keeps track.
Yeah.
The algorithm one, if you mention it, then it makes sense. Okay. How do you, without having some numbers, how do you even compute, the probability? It will be a question.
Yeah.
That will be, okay. So that I suggest. Yeah, go ahead. Yeah.
Yeah. So the verifx algorithm receives the set of K images. There is no trigger position given. We need to check if there's a trigger at some position. So what we do is for each position and for each image, we use abstract interpretation with deep poly to create constraints representing the trigger as a variable and the constraints that we have walked through in the example. And we get the constraints corresponding to a successful attack on all images in X. And
yeah, I mean, you could I would use it. You actually generate a verification condition file, okay? Which exactly if it is SAT, it will mean that successful now. So yeah, I mean, I guess it's okay. Yeah, that's okay. Yeah. Yeah, for each position, it generates for each image, for each position, right? It's both for each position. I mean, for each image, for each position. Correct. Yeah.
Yeah. And then
I think given set of, I guess that is for all. Yeah. There is 2 loops here for each position. Yes, fine.
There are 2 loops. One for the position, one for the images. So in the case the algorithm verify X finds that a trigger might exist, it uses, like I said, a gradient descent optimization approach to generate a trigger that works on the set X.
What you have here is, I guess this is okay. I mean, this is what, this is the top level view of the entire flow. Now you will get into each of these algorithms in detail, I presume. Yeah.
Yes.
Okay.
So I think I can skip this. I've talked about this and like we discussed.
You can go to the algorithm directly from now.
So this is the overall algorithm that's called. So we have the input parameters, neural network n, the attack success rate theta, the sample size k, and the shape of the trigger, number of channels, the height of the trigger and the width of the trigger. You have the target label that you want to look at attacks for, and you have the parameters corresponding to the hypothesis testing, type 1 and type 2 error, and the indifference region width.
Also, the hyperparameters for the hypothesis testing.
Yes.
Hyperparameters.
So we initialize 2 variables to keep track of the trials, so-called trials that we do as part of our hypothesis testing. So n will be the number of times verifx is called. So it's the number of trials. And z will be the number of times verifx returns safe. This will count as evidence towards the null hypothesis. That is that the network is safe. That is, there is no backdoor attack with at least theta success rate on the subset X. So, and we initialize P0 and P1 as the probability boundaries corresponding to H0 and H1. And delta we use it because
the subset X you mentioned. Okay, that was a bit confusing. What do you mean subset X? What is X here?
So if you have, like, let's say
those X is the images, okay? Randomly selected images, okay? Which they don't know. I mean, of course, line 6 says that. So maybe in verify X, because X is a parameter to verify X. You might want to, when you say that, the set of randomly generated images of size K. Okay.
I will lead with that.
Okay.
So
small point, not a big deal. Go ahead.
So what we do is we repeatedly perform trials. So we increment the trial count n, and we sample the set X containing K images from the data set. And then we call verify X, which is deterministic. It takes the neural network, it takes the subset X, takes the position of the it takes the shape of the trigger and the target label that we are trying to attack. So verify X, like we discussed, and we'll see the details of it. It returns either safe or unsafe or unknown. So let's say it returns safe. Then, like I said, it counts as an evidence towards the null hypothesis that the network is safe. So we increment Z. Otherwise, if the if verify X returns unsafe, it must have also tried to generate a trigger. So what we do is we try to see if that generator trigger satisfies the success rate on the test set that you might have. Because we only generated a trigger that works on the subset X, we want to see if this is an actually a good enough trigger for the whole test set. So you take the full test set, you run it with this backdoor trigger, and you see if at least theta of them are attacked successfully. In which case, we can return unsafe because we found a trigger that works on theta fraction of the test set that you have.
Yeah. Now this one you will describe separately, okay? How exactly you will generate the trigger and what that success rate means. Yeah.
Yeah. So the last 4 lines correspond to the SPRT algorithm. It basically looks at the likelihood ratio that the data you've seen so far is what's the likelihood that the data is.
I mean, I have one question here.
Yes,
Since
sir.
verify X can return safe, unsafe, and there is an unknown case as well.
Yes, sir.
Where is that handled here?
So it counts as evidence anyway because we have not incremented Z, right? And when we measure the likelihood ratios, if we see enough
I guess
cases,
if verify X is true, then it returns safe. Else, if verify X is false, okay, then you return unsafe. But verify X can also return unknown, no?
Yeah.
Then it will, I guess, fall through, and you will come.
Yeah.
Huh?
Yeah. We'll just go to a next trial unless we reached some critical probability ratios according to SPRT, by which we can either accept H0 or H1.
Yeah, I think there is that question. I mean, unknown means you will come here, then you don't increment. In that case, you don't increment. You will increment N, but you will not be incrementing Z. That's all.
Yeah.
That's all. I think that's, okay. So, but then you will, you will not be including it. Okay. Yes. Yeah. That is what the Z will not be incremented in that case. Okay.
Yes, sir. Yeah. So like I said, the last 4 lines correspond to checking for the likelihood ratios in cases where H0 is true or H1 is true, comparing them to certain boundaries based on the type 1 error and type 2 error thresholds you're willing to accept. And based on that, you either accept H0 and return the network is safe, or you accept H1 and you say you don't know if the network is safe or unsafe.
I have another question here.
Yes, sir.
Does this algorithm guarantee to terminate?
The paper uses a timeout actually.
Okay, that's something that you mentioned because there's no guarantee that it has to converge to these 2 things, no?
Yes, sir.
It may never converge, right?
Yeah. You might have some combination of K that makes you.
And then you might have to get out.
And you'll be stuck in that region between these 2 probabilities.
Okay.
Yeah.
Good. Yes.
And so the next step of level of detail is to look into the verifyX algorithm, which is more deterministic. So you receive the network and you receive the subset of images X of size K. You receive the shape and the target label. And we use a flag Boolean flag to keep track of the case where we don't know if there is a successful attack or not.
By the way, why would verify X return unknown? Why would unknown be a possible outcome?
Because we're using a over
Good.
approximation
That's
method,
what.
right?
Yes.
Yeah.
I was just testing you. That's it. Yeah, over approximation. Therefore, it may not. Okay.
Yeah.
It may fail, but you don't know, right?
Yes,
That's
sir.
why. Yeah, you will have to then. Yeah, there is an unknown case. Yeah. Okay. Go ahead.
Yes.
Mhm.
So in the outer loop, we loop through all possible trigger positions, and in the inner loop, we loop through all the images. And this order is important because we want to find attack at a specific position. So we make sure that when we are building up constraints for all the images, we are making sure the constraints have the trigger at the same position. So we have the
That's why
five.
I like to
Yeah.
call this phi as a verification condition. I mean, it's also a constraint that that exactly captures the thing. If it is unsat, it is a condition. If it is unsat, then which means that there is no attack, free of attack. Okay.
Yeah.
If it is sat, then it is thing. So it is a verification. It's kind of that's why they call it attack condition. Okay. So it's exactly captures that thing. Yeah. Okay. Yeah.
Yeah. That's true. Yeah.
Yes. Yeah.
So phi pre is the precondition that we have. And what we do is we initialize the
What is the precondition?
actually I can't remember. So there's one precondition on the input based on what the values are. And
that's what it is. It is the precondition on the inputs. Okay. So like you showed in that example, I mean, there are constraints on the inputs, and that's what will be part of that. Yeah.
Okay. Yeah. Okay, that makes sense. Yeah. And yeah, attack condition will propagate it using deep poly. So what we do is for each image in the subset X, we generate an attack condition using deep poly. Yeah, which includes the important output success condition where the logic corresponding to the target label TS should be greater than all other labels. And we call a SAT solver, and if it results in unsat, then we can break away because there's no way the rest of it doesn't matter what the other inputs conditions are, if they're satisfiable or not. And suppose assume phi I is not unsat. So we get a bunch of constraints conjuncted for each image, and we try to solve it. And if it results in SAT, then we might have a model that actually works on the subset X, or it might not.
Yeah, I think there is a little bit thing that you glossed over. Okay, so the idea here is you're breaking only out of the inner loop. Okay.
Yeah, we only break out of the inner loop. Yeah.
But then you're assigning phi to be false. The more maybe no. In that case, you're breaking out of the entire thing, I think.
Yeah, because this will anyway result.
Because the entire thing will be false. And why are you doing it like that? Why is it okay to break out of that entire loop? Because why? Because
so this is saying
yeah. Say that again. Yeah. Why?
So because if this is unsat, then this what we get by doing line number 10 can be sat. So we skip all the images. That's one thing. And then we don't have to check for this because
no. Well, intuitively, why? Even if this attack condition is false, okay, which means there is no attack, right?
Yeah.
That at that position.
Yeah, if it's unsat, then we know for sure that there is no attack at that position.
At that position,
Yeah.
but which means oh no, I'm sorry. The position for each trigger position is the outer loop. Okay.
Yeah.
Here, because you can get out of this because you're only looking for you have to, that for all images that there is an attack, okay, at that position.
Yeah.
That's why you remember that question that I raised earlier. That's why you don't need to check for any other positions anymore. Okay.
Yeah, we want to check for all
That
the
is the
images.
point that we'll have to do, and the accumulation is done only if there is attack. For all the images at that position. That's why you can set this to false, and then you can get out. If it is false, this will never be sat. Okay.
Yeah.
That is okay. So I think that you glossed over. Yeah. Now you understand, huh?
Yeah. If it's unsat, we can
Yes.
move to the next trigger position because we want to check for an attack that works on all the images in X.
That's why then it is no, as per because so for that reason, there's no point. You don't need to accumulate anymore any of the conditions in this.
Yeah. Thank you, sir. Yeah. So at the end of this, maybe let's say we did not encounter any image constraint that resulted in unsat. So we have a bunch of conjuncts corresponding to each image. We're calling it phi.
Yeah.
Let's
When
say
you come out at 11, Shashank, okay, what is it that you can guarantee? What condition can you guarantee about attack for all X? Okay, that there is. What is it? What is the condition that is guaranteed here at 11?
You can say that there is phi is not unsat.
No. Say it more intuitively. Okay, obviously it is.
Unsat corresponds to safety. N being safe with respect to X.
Yes. Okay. Yeah. So when you do that there, then
it means for that position, we might have a trigger at line 11. If line 11 is true.
Well, which means that there will be, okay, one or more X's at that position is guaranteed to have an attack. Okay. That's what is happening, right? Yeah.
It's not guaranteed, but it's possible.
It's possible because it's over approximation, but then that's why there is unknown also. Okay. You're right.
Correct.
So I think saying that would help. Okay.
Yeah. So
otherwise, what will happen is this if itself will be skipped and you will go to unknown, right? Yeah.
You'll go to like next trigger position or we'll come out.
I mean, I was testing you and you use that to explain it correctly there. Yeah. Okay.
Yes. So let's say we think we could not tell the network was safe. So we might, since it's an over approximation, we know that there might be a trigger. So what we do is we use another method called OP trigger that optimizes for a trigger that works on the subset X. So if this optimization method can return
one doubt that I had, here you're calling SAT on that accumulated phi condition, right? For each images, on which there are things. Okay. Then if there is a SAT, why would there be an unknown here? SAT will either say it is SAT, or if solving phi results in SAT, he says or unknown. Why would there be an unknown?
So solving, let's say we call a SAT solver on phi. It either returns SAT or unsat. But in this case, we know it returns SAT. But we take the actual example that the model returns, the SAT solver. And if we test it on the subset X,
No, my question is about
it might
why
not
does
be an
he,
actual example.
why does he say SAT or unknown? If phi results in SAT or
Because it could be a
unknown,
false, it could be a counter example, sorry, false.
then he would have, no, SAT, if it is SAT, why unknown? I mean, when you call SAT on phi, it always returns SAT or unsat, no?
Because 5 is an over approximation.
Even in that case,
5 is an over approximation, so we don't know if what.
yeah, but even
can,
in that state, it returns a SAT, but it may not be an actual counter example. So
yeah.
is that right? Okay. So how will you determine that? I
So
mean,
you can run it.
yeah, okay.
Can
That
do a
detail
forward
is
pass.
what?
Yeah.
Yeah, I was expecting. Correct.
Okay. Yeah.
So because there is some more work to be done because SAT solver itself will only give SAT or unsat. But since it's an over approximation, even a SAT may not be an actual counterexample, and that's why there is an unknown. Okay, good.
Yeah.
Okay.
Yeah. So if it results in SAT, we take the model written by the solver and we check if it's actually a trigger or on the network for this input set X. If it is, we could just return that. But if it's not, we are in the unknown case where we invoke an optimization method that then does this that tries to generate a trigger that works on all inputs in X.
Again, that is kind of a statistical method with loss function and so on, right? Yeah.
Yes. I have that in the next slide.
Yeah.
So if it returns a trigger, we can return unsafe. If it cannot, we know that we could not verify that this position at this position HPWP that
Yeah,
the network is
that's
safe.
why, what you had stated much earlier in one of the earlier slides, this trigger itself is being generated with a certain success rate. Okay. Yeah. With a certain success. That's why it's statistical in that sense. Yeah. Okay, good. Yeah. We still have time. Go ahead. Yeah.
So in the final line, we check if we have ever set has unknown to true. If yes, that means at some position, for some position in the input image, we could not verify that the network is safe, and we could not generate a concrete trigger to show that it's unsafe. So we cannot return safe or unsafe. So we'll have to return unknown in that case. In the other case, it means we have checked all possible positions, and it must be that we got that phi I was unsat. At least one phi I was unsat in every single for every single trigger position.
Yeah, I mean, yes. For all images. Yeah.
So they have not given the listing for algorithm 3, so I've tried to outline it a bit. So the OP trigger function takes these inputs and either returns a trigger that works on the subset X or it returns null. So we had, before calling this OP trigger, we had tried to SAT solve phi. So if it returned SAT, let SM be the solution that's returned by the SAT solver for phi. And if this solution, the trigger, if it works for all the images in the input X, then we can just return SM. Otherwise, we calculate a loss function.
But how do you check this? This is another SAT call here, no?
Which one, sir? Line.
It works for all X. How do you check that?
Oh, you just do a forward propagation on the batch X and see what label it outputs for all images.
So that's
it must be
forward
equal to
propagation on
TS.
all X's you do. Yeah.
So if
otherwise you have some go ahead.
So otherwise we try to calculate loss, which is basically So for each image, we look at what the network, what label the network assigns to the image. And if it's the label is corresponding to the target label, then we give a loss of 0. If the label is not corresponding to that, we take the difference.
I think it's slightly different than that. I think they use some kind of a measure, how far it is. Okay. They have some tolerance, epsilon or something like that. It's not exactly whether it is equal to that label or not. How far it is from that desired label. And I think they use that, no?
They use that measure in case the output label is not the target label.
Oh, okay. But well, you don't have that here at all, no? Where do you have that measure here in this?
Yeah, maybe I'll write an equation for loss here.
Yeah, or you should mention in words, okay?
Yeah.
Loss itself uses some measure to see how many of them are, at least close enough, okay?
Yes, yeah.
Yes,
yeah.
That's what you have to say. It's not exactly equal or not equal, how close it is, okay?
Yeah, because we're looking at the logits, Yeah, so we take that loss and sum up across the set X, and we try to minimize it using gradient descent. And we try to get a trigger for a potential trigger for using this optimization approach. And again, you can check if this optimized trigger works for all the images in X by doing a forward propagation. And if it works, we can return it. And if it doesn't, we return null. So there's a proof of correctness that we want to show. So the statement that we want to prove is given a neural network N, set of images X, the shape of the trigger and the target label TS. We want to show the verify X correctness. That is, verify X returns safe only if there is no backdoor attack, which is successful on all images with the provided shape and the label. And it returns unsafe only if there is a backdoor attack, which is successful on all images with the given shape and the target label. Okay, so the proof at a high level is that we use the correctness of the T-poly, which is that attack condition always returns a constraint, which is an over approximation of the exact constraint that must be satisfied, such that the trigger is successful on a given image N. So, so if you recall the algorithm, verify X returns safe only if constraints that must be satisfied to attack all images in X at a given position or at each position or unset. So this is the argument for the first half of the statement. And the second holds because we return unsafe only when we're able to generate a trigger that is successful on all images in X.
Yeah, I think that soundness is correct. So there could be, in all other cases, you just return unknown, right? Yeah.
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 So there's a proof of soundness also. So we want to see that given the network, the success rate, the target label, the shape, and the different parameters for the verify PR algorithm, we want to show that the verify PR returns safe only if there is sufficient evidence that there is no backdoor attack with the success rate at least theta.
Yeah, maybe you should remove this parenthesis.
Yeah, I think it's very loaded. Yeah. So the way we do is we rely on the correctness of the underlying SPRT algorithm. So we assume we are doing the SPRT algorithm correctly. We are counting the trials and the successful trials correctly. And yeah, so we assume verify PR return safe only if there is a sufficient evidence that H0 is true. So we saw how the probability of not having an attack on a set of K sampled images is at least 1 minus theta K. But we also know that if there is a backdoor attack with theta success rate, then if you take K random images, the probability of having an attack on all of them is theta to the power K. So if we take the contrapositive of this statement number 3, and we do modus ponens with statement number 2, we get the conclusion that there is no backdoor attack with success rate greater than or equal to theta. So we use the SPRT algorithm's correctness to prove that verify PR also returns correctly. Yeah, so the final part of the section is where they've done experiments on using actual implementations. So they use about 51 networks. 45 of them are like fully connected networks with varying hidden layers and width of the hidden layers, and 3 different activation functions. And they also use these networks which are larger and that are also trained with 2 approaches called diff AI and PGD. I've not read into them, but from what I understand, these methods are supposed to make your network robust to adversarial attacks. So they were trying to see, I guess, if they're also useful in making them robust to backdoor attacks. So the trigger they used was the shape of 3,3. And they used MNIST with a test set of 10,000 images. Yeah, so they tried to answer 4 broad questions. Question number 1 is, what is the effectiveness of the VerifyX algorithm, which they tested on 100 images, about 100 images per network cover target label pair. Then they look at how effectively can we verify the absence
How
of
did they
backdoor.
test? How did they test the effectiveness? What does it mean to test effectiveness? What is it that they measured there? That you say tested on 100 images.
Yeah.
But what did they measure there? Yeah, as an outcome. Or you're going to tell what that thing is, or later?
Yeah, I have like I show you like what are they
well,
measuring the success
yeah, but
rate.
informally, there
Yeah.
was, what is the effective for? I mean, how many times it was able to tell there was
It was safe.
safe or unsafe?
Yeah, so if I give a clean network.
If it gives unknown for a lot of things, then it is not that effective. Correct?
Yeah.
Okay. That's what I'm.
Yeah, how reliably can it tell if I give a safe network, can it tell me it's actually safe? It's kind of what I understand.
No, it is always sound. Whenever it gives safe, it is sound. You already proved that. Okay. Whenever it gives safe, it is safe. Whenever it gives unsafe, it is unsafe. Okay. Effectiveness means if it gives a lot of unknowns, then you can't answer it. That's all. Because you've already proved that verify X is sound. Through that lemma.
Yeah.
That is, it never says whenever it says safe, it is safe. Okay. Whenever it is unsafe, it is indeed unsafe. Okay, that you've already showed in that lemma. Therefore, by here, effectiveness means, if it is already able to give that when it is no, there is no backdoor attack. I think that's what it is. Okay, go ahead. I mean, I'll ask the question later on. Okay, go ahead. Yeah. But there will be that question about what does it mean to be effective. Then second is.
So second question is to see if we can verify backdoor absence with specific success rates using the verify PR algorithm. So they try a combination of success rates and sample sizes with certain timeouts set. Yeah, so and then they look at the time efficiency by measuring the average wall clock time that the experiments took while answering research question 1 and research question 2. And finally, they look at can we generate backdoor triggers when the network is actually unsafe? And they use
And I
and
have
they-
a question here. Is just K size 510 is large enough? That seems awfully small, no? The number?
I would say it's probably timing out with the larger
Okay, let's see. Yeah.
sample size. Yeah. So they look at how effectively can they generate backdoor triggers when the network is indeed unsafe by actually taking backdoor networks trained through data poisoning. And then, they stamp a white square and assign a target label and then train it. This is the method to train the backdoor networks. And by evaluate only if the backdoor attacker success rate of at least 80%. This basically means the test set was filtered to find images susceptible to this backdoor. Basically, all the images that were not being attacked successfully, they removed it from the.
Yeah, but how come they used such a large number of networks for this? But I don't know how many, they use only a very small number of networks for answering these things. Yeah.
They did use 45 or more, I think, even in research question 2. Oh, wait, no. For the research question 2, they used a small subset. For 1 and 4, they did use 45 networks.
Oh, I see. Okay.
Yeah. So on the y-axis you have the x-axis you have something like ReLU_3, which corresponds to a network with ReLU activations with 3 hidden layers.
And what is cross 5 means? 3 cross?
There are 5 such networks.
Oh, okay.
Yeah. So you have 5, and then you have 10 possible target pairs or targets. So you get 5 into 10, 50 pairs of network cover target. So all these networks are clean; they're not backdoored. So we pass this to verify X and see if it actually returns safe. What they've observed is that it succeeds. It does well in the case of less complexity, and it somehow finds tannage to be a challenge. And the authors suggest it could be due to over approximation in the case of tannage being too powerful.
Can you explain what this you're going to say? 455 out of 510 verification tasks and 89% success rate. What does that mean?
So if you look at the
all the thing put together, there
Yeah.
are 10. Okay.
Yeah.
Out of which 455 were verified with success rate means you don't mean the probability. It
No,
is-
no.
No.
Yeah. So I mean, all these 510 networks are safe. Like 510 instances of the network cover target pairs are safe because there's no backdoor. But the VerifyX returns safe only in 89%
Mhm.
of the cases.
The rest of the case, it says unknown. Yeah.
Yeah.
Mm.
I think like K was about 100 here. Yeah, they used to, it's a large K for this question. Yeah. The second question is to look at the effectiveness of the verified PR algorithm. Yeah, so the question is, does the complete approach successfully verify that the networks are free from backdoors at a certain success rate theta? So they try, so they tried,
Yeah, success rate is actually with theta. Okay.
yeah.
Mm.
So this they conducted tests using all 10 target labels for each network, and here in the x-axis relu underscore 3 underscore 10 corresponds to 3 hidden layers and 10 neurons in each hidden layer. Yeah, so the thing of interest to me was like increasing K or decreasing theta resulted in timeouts. And this, as I understand, is because yeah, it increases the probability term by increasing K and decreasing theta increases the 1 minus theta to the power K probability term. And this leads to needing more rounds of hypothesis testing. So yeah, so increasing K or decreasing theta resulted in timeouts that I've said. And one anomalous result that they have found is that for tan H, 3 layers and 10 neurons per layer, yeah, like they were able to generate triggers with
but
more
here the
than
question is, here they were, obviously they must have used benchmarks where which were not safe, which were all had backdoor.
no, sir, they used
Yeah.
clean networks in this question also.
They use clean networks. Oh, in
Yeah.
all these cases, they use clean networks. But that's why varying K is important here. Yeah.
Yeah. Yeah.
Uh,
Yeah.
Yeah. So if you decrease theta, you get more assurance, but it times out. Okay.
Yeah. Yeah.
Mhm.
Yeah. So yeah, I was saying, the anomalous result is that they were able to generate triggers with
I think one thing is they use a high theta. What does that mean? Okay, in terms of those SPRT algorithms, a high theta will mean it is if it says that probability, success rate probability will with great assurance, is it? Okay, what does that mean? That's what I was. Because the probability, the way the SPRT algorithm, it is not clear to me for a high theta, if it says, what does that mean? I mean, how confident can you be about, but you should be able to get, yeah, with the probability of not having an attack on a set of K randomly set of values is more than 1 minus theta to the K. Okay. Which means with the high theta and low K, something that you doing.
Yeah, so I think theta can be thought of as the strength of the attack. And like decreasing theta corresponds to us considering a weaker attack as a possibility. And a weaker attack has a smaller chance of succeeding on a single image.
See, suppose you should choose for argument's sake, theta is equal to 1, K is equal to 1. This will be 0, huh? What does that mean? So to choose
If
theta,
theta is 1, it means the attack will always be successful.
huh?
So the probability of not having an attack will be 0.
This makes sense. You will have to, then k is equal to 1 means your sample size will be only 1. What does that mean? You have to think a little bit about this. You have to choose, if you have big sample size, no, 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 no. Yeah, yeah, yeah. But I think it's not like just determined by that because they keep counting.
Yeah.
Yeah, they compute a probability now.
Yeah.
That will be probably it will fail. Okay. So if you have very small k, if you have k is 1, I mean either it is 1 or 0. Okay. So that p, what they compute, then p is some kind of a ratio of two probabilities there, right? We're going
Yeah.
to algorithm. Yeah. Yeah. Then you use some delta. See, the problem is if you choose z, if you choose k is equal to 1, then z, n will be 1 at most, right?
Uh,
No, that's actually not true. So you can keep calling of size k, and you can keep running it. Huh? Yeah, each time your sample size will be of set will be 1, but you will be, it is almost like you're doing one at a time, right? Yeah.
yeah. Yeah.
Then you may be getting a thing, but it will take a very long time. That's why those kinds of things will time out. Yeah. Yeah. No,
Yeah.
no. A large k it will time out. Yeah. Or small theta will time out. Huh?
Yeah. Because both of those will lead to, like, it makes it harder for an attack to succeed. Because you either have a large patch or you have a low success rate. Uh, so either increasing k or decreasing theta will lead to making it harder for an attack to succeed.
Okay, let's go move on to the thing. Yeah, let's into something to think about. Okay, what exactly these parameters mean is a little bit unclear. Yeah. So, how will you read this? Is this thing good or what? What does it say?
Uh, so it worked, it seemed to have worked well for the ReLU networks
Why would you say that for you it works good? Why?
because if you look at the indices corresponding to ReLU, and if you look at for different choices of k and theta, you're able to uh, correctly verify that there is that the network is safe uh, respect to that particular theta, as opposed to let's say sigmoid or tanh, in which case,
So, for example, let's take this tan H. Then you were hardly able to verify anything, no?
yeah,
With respect to ReLU, you were able to Yeah, because there were 10, you were almost able to verify with k is equal to 5. Yeah. Mhm. Okay. That's what, that is the thing. Huh? Okay. But I think I'm not sure how much, to wait to put on this because it took so few benchmarks, no?
Yeah, yeah,
The K variation is also not very large, right?
true,
Because
true.
it
Yeah,
times out. Increasing K or decreasing theta sometimes times out. Yeah.
yeah,
Okay.
yeah,
So I'll take this with a pinch of salt. Okay.
yeah,
Yeah, that is
yeah,
my, okay, go ahead. Next thing. So maybe that is,
yeah, makes sense. They also look at the efficiency in the case of time.
mm,
They look at the wall clock execution times for experiments in the
mm,
previous two questions. And uh, yeah, so this is the time for verify X, that is the
mm,
research question one. They look at K equals 100 for the 45 networks. And there's a huge variance in the wall clock time from 14 seconds to nearly 6 hours that they had to like plot it in log time scale. Uh, yeah, they found that TANH networks were significantly slower. Uh,
mm,
they attributed to complex verification or the precision loss in the over approximation. Uh, yeah, and for the other question, using wall clock time for the experiments in
mm,
verify PR. They found like uh, networks often timed out for as the networks got more complex. Yeah, it's uh, the running time where you can see 600 minutes being hit in multiple places, which corresponds to the timeout limit.
mm,
Like TANH with 50 neurons per with 5 layers, always timed out.
mm,
And going from k equals 5 to k equals 10 as expected increases the uh, duration, and going from theta to 0.9 to 0.8 also typically increase the workload time. And yeah, so they look at the final question, that is
mm.
to actually give a backdoor network, can
Trigger.
the approach find and generate the trigger?
Mm,
And they take a new set of 33 plus 12, 45 networks and use training data poisoning to insert a backdoor. And they filter the test set to have only the images that are susceptible to the backdoor attack. And they run the OP trigger function on these backdoor networks. Uh, and yeah, they find that for 33 out of the 45 networks, there was a trigger was correctly generated. And for the other 12 networks, the generation did not work because,
mm.
they say the data poisoning attack itself had not worked effectively. But they say the process itself was fast
Mm.
because it relied on gradient optimization.
What is the initial poisoning as opposed to data poisoning, where the initial poisoning attempt failed?
Oh no, I mean like the initial. So they just mean like these 12 networks are also data poisoned
Mm,
during training. Uh, and they saw that the OP trigger could not return a trigger. And when they investigated, they found out that the poisoning attempt itself was not effective. Um, like it had less than 80% success rate. So they say it's not reasonable to expect the trigger generation process to produce a trigger.
Because the quality of the trigger itself was bad, is what you
Yeah.
said.
Yeah,
Huh?
yeah.
These were the examples where the quality of the trigger was good. That's why. So, okay. Good. Yeah. So let's wind up. I think this is fine.
I think summary is fine.
Yeah. And that's okay.
Yeah.
Okay, we'll skip this. Good. I think I'm going to replace you with Lucky. So you will go tomorrow in place of Lucky.
Okay.
Yeah.
Okay.
Yeah. This
Yeah.
I think you are quite good and ready to go. Yeah.
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 So any final points, the main points that I should address?
No, I don't think, I have, I'll send you if you want, you can listen to it and then so on. I think I made most of the points. I don't think there is any need for you to change anything.
Okay.
This was good. Yeah.
Sure. Thank you.
Thank you for your time.